We continue now with the section 3.4 notes, and I just want to make a couple of concluding comments regarding example 2, which worked out at the end of the first video. The first thing is to notice that after we found that -1 was a root of this polynomial function f, that the remaining roots, which we found by solving a quadratic equation, 1/2 and -3, if you look at the list of possible rational zeros, notice that those two numbers do appear in the list. Positive 1/2 and -3 are two of the possible p over q rational zeros that we listed according to the rational zero theorem. So if you find additional rational number zeros, then those are going to appear in the list of possible rational zeros that you constructed initially. The second thing is that with a third degree polynomial, if you can find one rational zero, then the remaining zeros can be found by solving a quadratic equation, because the quotient that you're going to obtain, in this example it was 2x squared plus 5x minus 3, you're going to be able to find the remaining zeros either by factoring or perhaps using the quadratic formula. This equation that we get from the quotient after finding a zero is sometimes referred to as the depressed equation for the function. So it really only requires one successful synthetic division in the case of having a third degree polynomial to allow you to find any remaining zeros of the polynomial, whether they be rational or even irrational or not even real numbers. They can be found by solving the depressed equation, this quadratic equation. And this is something we're going to be using in the other examples as well. Moving on now, a very good approach to narrowing down the list of possible rational zeros obtained from the rational zeros theorem is to produce a graph of the polynomial function. And since technology makes this very easy, either using a graphing calculator or something like Desmos, which you have a link to through MyMathLab, you can easily produce the graph of the polynomial function whose zeros you're trying to find. And then just keep in mind that real zeros correspond to x-intercepts of the graph. And by looking at the x-intercepts, you can determine which rational zeros might be good candidates to be the actual zeros of the polynomial. So we're going to illustrate this with example 3. And let's begin by listing the possible rational zeros of this function. Again, you see it's a third degree polynomial. So we have our p's and our q's. And so the p's are the divisors of the constant term -2. And that would be plus or minus 1, plus or minus 2. The q's would be the divisors of the leading coefficient, which in this case is 4. That's plus or minus 1, plus or minus 2, plus or minus 4. So if we form all possible p over q's, if we take 1 and 2 and divide by 1, we get 1 and 2 again, plus or minus 1 or 2. If we take 1 or 2 and divide by 2, we get 1/2, 1 over 2, and 2 over 2 is 1, so we don't need to list that again. And then if we divide 1 and 2 by 4, we get 1 over 4. And then 2 over 4, which is 1/2, which again has already been listed. So the possible rational zeros of our function f of x are plus or minus 1, 2, 1/2, or 1/4. Now, to the right you see the graph of f, and let's pay particular attention to the x-intercepts. You can see we have 3 x-intercepts. That would tell us that there are 3 real zeros. I'm just indicating the x-intercepts here. And let's see if any of those x-intercepts match any of the numbers in our list of possible rational zeros. Let's look at the positive ones. 1, 2, 1/2, 1/4. You can see really none of those appear to correspond to any positive x-intercepts. There's a positive x-intercept between 2 and 3, but it's definitely not any of those numbers that we see there. What about negative possible roots? -1, that's not an x-intercept. -2, no to that as well. -1/2 doesn't appear to be -1/2. -1/2 would be right about there. So that doesn't appear to be an x-intercept. But -1/4 looks like a good candidate. Okay, that would be this x-intercept right there. So let's try, based on the graph, let's try -1/4. So what we'll do is we'll do this by synthetic division. I'm going to write the coefficients of f. That's 4, -7, -10, and -2. And bring down the 4, multiply -1, add -8, multiply +2, add -8 again, multiply +2 again, and indeed, there's 0. So -1/4 is a 0, and since this is a third degree polynomial, the quotient should be second degree. That's going to lead us to a quadratic equation. So let's take our quotient. You see the coefficients for -8, -8. That corresponds to 4x squared minus 8x minus 8 equals 0. Now we can simplify this. Oh, excuse me. One moment, please. I don't know why my computer does that sometimes. I'm hitting something with my hand, I guess. Anyway, we can simplify this by dividing through by 4. Okay, I'm going to just divide everything by 4. So x squared minus 2x minus 2 equals 0. Now what we would discover is this doesn't factor. So I'm going to make use of the quadratic formula here, and we have this is 1x squared, so we have a equals 1, b equals -2, c equals -2. And the quadratic formula, oh, there it goes again. Okay, the quadratic formula is, let me put this over here. X equals minus b plus or minus square root b squared minus 4ac over 2a. Okay, let me plug in the values from the equation over there on the right into the quadratic formula. Be +2 minus b is +2 plus or minus b squared is -2 squared, which is 4, minus 4. A times c is 1 times -2, which is -2. Take the square root of that whole thing, divide everything by 2 times a, 2 times 1 is 2. Okay, now we're going to simplify. It's 2 plus or minus square root 4 plus 8 over 2, or 2 plus or minus the square root of 12 over 2. Now 12 is 4 times 3, and the square root of 4 is 2, so this can be written as 2 plus or minus 2 times the square root of 3 over 2. And then since we can divide both terms by 2, we can write this as 1 plus or minus the square root of 3. So trying to find some space here, let me write down our conclusions. The real zeros would be, first of all, negative 1/4. That was one of the rational zeros. Then 1 plus the square root of 3. Now the square root of 3 is about 1.7. So that would be approximately 2.7. And 1 minus the square root of 3, which is approximately negative 0.7. So, 3 real zeros, one of which is rational and appeared in our original list of P over Q's, that's negative 1/4. The other two, however, obviously did not appear in that list. That's because they are irrational. They are real numbers. They occur as x-intercepts on the graph, but they are not expressible as ordinary fractions. They involve square roots, and so there's a pair of irrational zeros as well. Now, irrational numbers are real numbers. They can be expressed as decimals. So they are real numbers, but there's only one rational zero, two irrational zeros. Notice one other thing. Negative 1/4 corresponded to the x-intercept that's circled on the graph. The other two x-intercepts correspond to the irrational zeros, and you can see that does make sense. 2.7 does appear to be this value right here, and negative 0.7 would be this value right here. So if you see x-intercepts that don't correspond to any of the numbers in your list of possible rational zeros, what that indicates is that those would correspond to irrational zeros that might be expressible in terms of square roots. And sometimes we can find such zeros by using the quadratic formula as illustrated in this example. Okay, so we'll do one more example of a similar form using a graph in example 4. I'll begin that in the next video.